Martin from MDrive Services. Welcome to our next video. Today we will talk about multi-winding transformers and specifically about the winding connection or vector group. Winding connection or vector group, this is describing how the windings are connected inside the transformer with respect to each other and the phase shift that is typically required in the VFD applications to supply the rectifier and to eliminate harmonics. So here you see an example YY0D11 for a 12-pulse transformer with 2 secondary windings, and the goal is to understand this and similar notations. Let's look at the multi-winding transformers. Here are 3 examples. The first one is the simplest one, just a 2-winding transformer. So we have 2 windings, one on the primary side, one on the secondary side, obviously. The notation is often that we use HV and LV, so high voltage and low voltage, although the secondary side it can be medium voltage, but very often you find this HV and LV by the transformer manufacturers themselves. They often use those terms, so I use it as well, that you are familiar with that. So this is the simplest one, 2-winding. However, in the drive applications we often have transformers with more than just 2 windings. So here will be a 3-winding example. We have 1 primary, 1 HV and 2 secondaries, 2 LV windings. So there will be a 12-pulse rectifier supplied from such a transformer. Or we can have even more windings, like here we have a so-called 5-winding transformer with 4 secondary windings, LV1 to LV4, and they have a corresponding phase shift, and this is where this winding connection or vector group comes into the picture, how we describe this transformer in terms of winding connections of each winding and the relative phase shift in between them. Now I would like to talk about something which is called clock notation. It's a principle how the notation of the winding connections or vector group is noted. So there is an analogy with the clock, as we can see here. So the full circle is divided into 12 hours. Full circle is 360 degrees. So this is 12 hours, meaning 1 hour, this segment represents 30-degree angle. So if we have this 1 o'clock, 1 hour phase displacement between the windings, it means that they are 30-degree shifted. If we just have the 2-winding transformer, simple one like YD1 or DY11, then we have 30-degree phase shift in one or the other direction. Important is to note, it's maybe not obvious, but the notation is such that the positive direction of rotation is counterclockwise. So in the opposite direction than the normal clock is rotating. It means that 11, if it would be DY11, then the Y connected winding is 30-degree leading. Vice versa, YD1 means that the delta connected secondary winding is 30-degree lagging. So just keep this in mind, it's always counterclockwise. Now with the star or Y and delta connected windings, we can only achieve a relative phase shift of 30-degree or its multiple. So the smallest phase shift we can achieve is this 1 hour on that clock, and this 1 hour is 30-degree because we have the full circle 360, 1 hour is 30-degree. If we have a multi-winding transformer with multiple secondary windings, then we need relative displacement between the secondary windings that is less than 30 degrees, it's a fraction of it. Therefore we cannot just use the basic connections Y and delta, but we need extended connections. One of them is the zigzag. The zigzag is abbreviated from the star connection, and to each phase we are adding few turns of the other phase. So the original star is the black one, and we can see that adding few turns to each phase of the other phase, we are rotating the whole, like broken delta or zigzag connection, we are rotating it. So this angle, the original star connected winding would have this axis that is vertical, and the zigzag connection has this axis, this green dotted line, and we can see that there is the angle. So this would be the angle of this zigzag with respect to the original star connection. And in this way we can produce an angle, a phase shift, that is smaller than 30 degrees. It just depends on the number of turns. If we are only adding few turns, then we are just creating a little angle. If we put more turns, we make the angle bigger. So we are not bound to the 30-degree system and its multiple, but we can create almost arbitrary phase shift. Similarly, from the delta connection we can make a extended delta, the same principle, so we would also rotate the whole delta connection by a certain angle in one or the other direction, leading or lagging. We can have extended delta or we can have polygon delta. So those winding connections are very common in the multi-winding transformers where we need a relative phase shift less than 30 degrees. Now let's illustrate what we have just learned on two examples. So here we have a 3-winding transformer, or so-called 12 pulse. So the 12 pulse refers to the rectifier, but a 3-winding transformer supplying a 12 pulse rectifier, or a 5-winding transformer supplying a 24 pulse rectifier. For the 3-winding design, we can just use star and delta connected windings, because we just need 30 degree phase shift. So it could be, for example, Y0, D11. We have 30 degree phase shift in between the two secondary windings. So the D11 would be 30 degree leading, referring to the Y connected winding. But we could also have we could realize the 30 degree phase shift with two extended delta windings, so abbreviated from the delta, but one extended delta with minus 15 degree and the other one with plus 15 degree. We again have a delta, so phase shift, phase displacement of those two of 30 degree. This is what the rectifier needs. Normally the VFD does not care what is the winding connection. Relevant is just the displacement of the secondary windings. If we have this 5-winding transformer, then we already have to use those alternative connections like extended delta or zigzag, because here we need 15 degree phase displacement in between the secondary windings, which we cannot achieve anymore with just using star and delta connected windings. So here is an example, Y0, D11, and then we have two extended delta windings, D030, D1130. I use this kind of notation here. I mean, as we just explained, or as you have learned, 1 hour is 30 degree. I repeat it again, you have heard it multiple times, but 1 hour is also 60 minutes. So if we have angle of 15 degree, we can also represent it as 30 minutes. So 0:30 means it's just half an hour, 30 minutes, so it's 15 degree. In this case 15 degree lagging, and 11:30 would be 15 degree leading. So this is one example of a 5-winding transformer with the corresponding phase shifts and with the 15 degree that is required from the drive system point of view. So here we have an example of relatively complex transformer. This one can be called 7-winding transformer. So basically it has 1 primary winding and 6 secondary windings, supplying 36 pulse rectifier in this case. One possible notation, one out of many combinations, is this one, where we have Y connected primary and we have the 6 secondaries denoted as LV1 to LV6, and you can see some of them use the extended delta connection, so it's derived from the delta, and this additional phase shift is in the brackets, and then we have normal delta and we have star connection. If you want to better understand such complex notation, or to understand the principle of the winding connection, of phase shifting, how those multi-winding transformers are designed and how it works, then purchase one of our webinars that is dedicated to this topic, and there we explain it in detail. We show also a lot of examples, so you can practice a bit and you can get correct understanding. Thanks for watching.